Right now, you are watching the past. Every photon that goes into your eye left its source a few moments, hours, or even billions of years ago. The light from your screen had been on a very short journey. The sun's light took 8 minutes and 20 seconds to reach your eye after it left the sun's surface. When you look at the moon, you're seeing the moon 1.3 seconds in the past. Look up at the stars tonight. You are looking at long ago. Sirius, the brightest star in our night sky, is shown to you what it was 8.6 years ago. Betelgeuse, the red giant that forms Orion's shoulder, shows us an image from 550 years in the past. You are not now seeing these stars as they are. You are looking at them, literally, frozen in time that has traveled across the cosmic void. This is not metaphor or poetic language. This is a literal truth about distance and observation. At a speed of roughly 186,000 miles per second, or 299,792 kilometers per second, nothing in the universe is faster. This speed limit of the universe, found and confirmed through centuries of observations and theoretical physics, means that information can't travel instantaneously through space. Every time you look at anything that isn't right in front of you, you're looking at history. The older the image you see, the further away the object is. It is this essential connection between distance and time that turns astronomy into archaeology. When they aim their telescopes at distant objects, they are not merely measuring space between. They are looking back in time. They are looking at the universe at earlier and earlier stages of its evolution. A galaxy 1 billion light-years away is seen as it was 1 billion years ago. A quasar that lies at a distance of 10 billion light-years shows us what it was like when the universe was less than a quarter of its present age. The most distant objects that our instruments can see give us images of the cosmic dawn, when the first stars were born and the first galaxies were forming from cosmic gas. This poses a deep question at the nexus of observational astronomy, cosmology, and fundamental physics. How far away is the furthest thing we can see? What is the most distant object, entity, or event that we can detect with our technology? Where does measurement end and the immeasurable begin? The answer tells us not only the size of the observable universe, but fundamental principles about what space and time are and how cosmic history shapes our own knowledge of the universe. You might be forgiven for thinking the question has a simple answer. Light has been traveling towards us since the beginning of time, approximately 13.8 billion years ago. So the most distant we can see is 13.8 billion light-years away. It seems like sound reasoning. It reads as if it were just a direct consequence of the finite speed of light and the finite age of the universe. But this simple calculation misses something crucial about the nature of space itself. The universe is not the static backdrop against which cosmic drama unfolds. Space expands, stretches, grows. This distance, however, is not the real distance that something is away from us, or that light travels. That commoving distance, how far away the edge of the observable universe is in all directions, is 46.5 billion light-years. So it's not that the observable universe is 93 billion light-years across, because that's how far light has traveled since the beginning of the universe. It's that the radius of the space from which light has had time to reach us since the Big Bang is about 46.5 billion light-years. This figure looks impossible on the face of it. How can we see objects 46 billion light-years away when the universe is only 13.8 billion years old? How did light travel further than it should have been able to given the time light had available? The answer has to do with what distance really means in an expanding universe. When we look out at a faraway galaxy, the light we see now left that galaxy billions of years ago. But in transit, space was itself expanding. The galaxy that emitted the light has moved farther and farther away from us through cosmic expansion in the light's travel time. The distance the light traveled is not the distance to the galaxy at the present time. The light may have traveled for 13 billion years, but the object that emitted the light is now located well beyond 13 billion light years because of the expansion that took place over those 13 billion years. This difference between light travel time and comoving distance is very important. Light travel time tells you when the photons started out on their journey, which is the age of the image you are looking at. The comoving distance tells you where the object is now if you could freeze the expansion of the universe and look at the object in the present day. For very far away objects, these two measures differ greatly. A galaxy whose light traveled for 13 billion years to get to us might be 30 billion light years away now. The expanding universe has been carrying it away since the light left. The equations governing cosmic expansion come from Einstein's general relativity. The expansion rate of the universe, or Hubble parameter, also known as Hubble constant, tells us how fast the universe is expanding as a function of distance. Current observations place the value around 70 kilometers per second per megaparsec. This means that space is expanding at a rate of 70 kilometers per second for every megaparsec of distance, 3.26 million light years for each second. For very large distances, this rate of expansion can exceed the speed of light. This does not violate relativity because the galaxies are not moving through space that fast. Instead, space is expanding, and the galaxies are carried along with it. The distinction is important and commonly overlooked. Cosmologists express this expansion using a quantity called the scale factor, which measures how distances between distant objects change over time. The scale factor is defined to be unity at the present epoch. In earlier times, the scale factor took lower values and distances between objects were smaller. In the future, if the expansion continues, the scale factor will have a larger value. The time dependence of the scale factor is determined by the contents and geometry of the universe, and in particular the ratio matter, radiation, and dark energy. The accelerating expansion is driven by dark energy, an enigmatic fluid that makes up nearly 68% of the universe's total energy density. Discovered in 1998 from the observation of distant supernovae, dark energy seems to be an attribute of space itself. As space expands, dark energy is created, and with its creation, expansion speeds up. This acceleration has profound implications for what we can see, both now and in the future. It causes horizons beyond which observation is not allowed, not because our instruments are inadequate, but because the very fabric of space-time forbids it. And the route to that is cosmic expansion. Depends on what you mean by seeing. If we limit ourselves to electromagnetic radiation, to photons of any wavelength that our tools can capture, then the furthest thing we can see is not a galaxy, not a star, not even a one-off astronomical body. It is a glow of ancient light that permeates all of space, incident on us from all directions. This radiation, known as the cosmic microwave background or CMB, corresponds to light emitted about 380,000 years after the Big Bang. From it, photons can arrive directly at any time in the past. Yet before we go into any detail about the CMB, we need to understand why we can't see anything older by the same means, i.e., using electromagnetic radiation. The universe was dark in its infancy. In the first few 100,000 years after the Big Bang, the universe was a searing hot, dense plasma of protons, electrons, and photons. The temperature was up to several thousand degrees Kelvin during this epoch. At temperatures like these, electrons are free and do not combine with atomic nuclei. These free electrons constantly scatter photons by means of Thomson scattering. A free electron can receive momentum from a photon and be deflected when they collide. In the dense plasma of the young universe, photons could not go very far without hitting an electron. Then they scattered. The mean free path, the average distance traveled by a photon before scattering, was only about 1 meter. Compare this to the height of the observable universe then, which spanned millions of light years. The photons were trapped. They constantly bounced off electrons. They could not diffuse freely through space. This remained in effect until the universe became cold enough for electrons to bind with protons to form neutral hydrogen atoms. This change, called recombination, even though the particles were only combining for the first time and not reincorporating, takes place when the universe reaches 3000 Kelvin. At this temperature, electrons can bind to protons to form stable hydrogen atoms. Electrons are bound in atoms. The density of free electrons plummets. The mean free path of the photon increased significantly. All of a sudden, photons could travel through the universe without scattering. Cosmologists call this moment when the universe became transparent, the surface of last scattering. The photons didn't stop scattering before this moment, and no direct observation is possible. After this moment, the photons were able to propagate freely over cosmic distances. The CMB is composed of photons that were emitted at recombination and have been free streaming through space ever since, now arriving on our telescopes after 13.8 billion years of travel. The CMB was not observed until 1964, when radio engineers Arno Penzias and Robert Wilson stumbled upon the unexpected microwave noise with a horn antenna at Bell Telephone Laboratories in New Jersey. At first, they blamed the signal for interference, maybe from pigeon droppings on their antenna. After they cleaned the equipment and ruled out all potential sources of noise, the signal remained. They had unknowingly stumbled upon the cosmic microwave background, the afterglow of the birth of the universe. The 1978 Nobel Prize in Physics was awarded to Penzias and Wilson for the discovery. The existence of the CMB had been predicted many years prior by physicists studying Big Bang cosmology, including George Gamow and his team. They reasoned that a hot, dense early universe should currently be bathed in thermal radiation from the distant past. Over the course of billions of years, expansion would have cooled this radiation. Their prediction was for a current temperature of roughly 5 K. The actually measured temperature, 2.725 Kelvin, was close enough to verify the basic prediction and make the Big Bang model the standard description of cosmic history. The CMB is observed from every direction at essentially the same intensity. If you were able to look at microwaves, you would see the whole sky is illuminated by this very old light. It differs by only 1 part in 100,000 in different directions. This exceptional smoothness tells us that the young universe was extremely smooth and uniform in all directions. Matter was distributed uniformly in all directions, with only minute density variations. Those minute variations, imperceptible in the CMB temperature map, hold great significance. They are the seeds of all cosmic structure. Slightly over-dense areas in the early universe had a bit more gravitational pull. Over billions of years, gravity has enhanced those contrasts more and more. Dense areas are drawing in even more matter, becoming denser. Underdense regions gave up matter to the surrounding regions and became voids. The clusters of galaxies, filaments, and voids of the large-scale structure of today's universe all arose from the small perturbations imaged by the CMB. Several space missions have produced ever more precise maps of the CMB. Launched in 1989, the Cosmic Background Explorer, or COBE, provided the first full sky map of the CMB temperature with useful detail. Launched in 2001, the Wilkinson Microwave Anisotropy Probe, or WMAP, enhanced the resolution and sensitivity by orders of magnitude. The Planck satellite, operated by ESA from 2009 to 2013, provided the most accurate measurements ever. These missions made cosmology a quantitative science. Data from these and other satellites enabled cosmologists to pin down cosmic's parameters with stunning precision. The age of the universe, 13.797 billion years, with an uncertainty of just a few tens of millions of years. The makeup was about 5% ordinary matter, 27% dark matter, and 68% dark energy. The shape of space, which looks flat or nearly so on large scales. The current expansion rate, as characterized by the Hubble constant. And all of these basic features of our cosmos are now known to several decimal places, thanks to measurements of the subtle patterns in the CMB. The CMB photons arriving at us today started their trip 13.8 billion years ago, but the comoving distance to the surface of last scattering is about 46 billion light-years. This seeming contradiction is resolved by taking expansion into account. The photons traveled in an expanding space. The patch of sky which emitted the CMB photons we see today was only about 42 million light-years from us when those photons were last scattered. During the 13.8 billion-year journey of the photons, cosmic expansion has pushed that region to a distance of 46 billion light-years. The CMB is the most distant thing we can see with electromagnetic radiation. Neither of us has seen a photon that contained information from even earlier time. Universe before recombination was opaque. That era's photons have been scattered so many times that they do not contain any information about their original source. The CMB represents a thick, opaque shell in time, beyond which we cannot make electromagnetic observations. It's the oldest light, the most ancient signal, the ultimate frontier of photon-based observation. But the CMB is not quite the furthest thing we can see. If we stretch the definition of what counts as electromagnetic radiation, other kinds of particles separated from matter before photons, enabling views even more ancient eras. Neutrinos, ethereal particles that barely ever interact with normal matter, decoupled roughly 1 second after the Big Bang. Until then, the neutrinos were in thermal equilibrium with the rest of the cosmic fluid, interacting regularly via the weak nuclear force. Once decoupled, neutrinos flowed unhindered through space, much the same way photons would several eons later. The cosmic neutrino background, or CNB, should permeate the universe in the same way as the CMB. These relic neutrinos today would be chilled down to a temperature of about 1.95 Kelvin, which is a bit cooler than the CMB. It would be around 56 neutrinos of each type for every cubic centimeter, but this depends on neutrino masses which are not completely known yet. The CNB has never been directly observed because neutrinos are so weakly interacting that no detector sensitive enough to do so currently exists. However, the presence of the CNB is very well established on theoretical grounds and also by indirect influence on other observables, in particular the CMB itself and the large-scale structure of the universe. If we were able to detect the CNB, we would be looking at the universe as it was 1 second after the Big Bang. The comoving distance to the neutrino decoupling surface would be somewhat larger than the distance to the CMB surface, but the difference is tiny on cosmic scales. The CNB exposes us to even older times than the CMB, but this window of observation is closed due to our inability to detect such low-energy neutrinos. Now, the waves of space-time itself have been found for studying the very early universe. Pulses are, however, tides, warps in the fabric of space-time, just like matter and radiation waves, which can interact with one another. More important is that they travel essentially unimpeded through matter. Potentially, gravitational waves could be even older than both the CMB and CNB, as they might be coming from the first fraction of a second after the Big Bang. Cosmologists expect the universe to have experienced a period of exponential expansion known as inflation in its first tiny fraction of a second. Quantum fluctuations in space-time during inflation were blown up to cosmic sizes and produced gravitational waves. Primordial gravitational waves would have a distinctive spectrum and polarization pattern. To detect them would be direct evidence for inflation and would tell us about the state of the universe at times as early as 10 to the 36th seconds after the Big Bang. Primordial gravitational wave searches are particularly focused on the imprint of those waves in the polarization of the CMB. Among the distinct signatures that would have embedded were gravitational waves which generate a particular pattern of polarization, called curl or beam mode polarization, in the CMB. This signal will be sought by a series of experiments including ground-based telescopes and several space mission concepts. There have so far been no confirmed observations of primordial gravitational waves, but they are still being sought with increasingly sensitive instruments. No signal other than gravitational waves can travel to us from earlier times. At sufficiently early times, the universe was so hot and dense that even space-time itself may have behaved in ways not described by classical general relativity. Quantum gravity effects become important at energies of order of the Planck scale, reached at t equals 1043 seconds after the Big Bang. Before this Planck time, our current understanding of physics breaks down. We have no accepted theory of quantum gravity to tell us what happened, or even whether time itself existed in any meaningful sense. The Planck time is a hard limit beyond which analysis becomes not merely unrealistic, but perhaps even incomprehensible. But it is not a limitation of our instruments or of physics. It might be a basic horizon where even the question what happened ceases to have an unambiguous answer. I think time itself may have originated from a quantum gravitational phase, which is beyond the description of our present framework. Going back to observable signals, the CMB is the most distant we can currently see in the electromagnetic spectrum, and probably the most distant we ever will see unless the CMB is detected or primordial gravitational waves are found. But astronomers have spotted individual objects at mind-boggling distances in the post-recombination universe past the CMB and into our own time. While these objects are not as far away as the CMB, they are still our most distant observations of individual objects, like galaxies and quasars. The farthest individual objects ever observed are galaxies that formed within the first few 100 million years after the Big Bang. These galaxies are the first generation of star formation in the history of the cosmos, the point at which the universe went from being dark and neutral to one filled with light from stars and reionized by their ultraviolet radiation. Observing such early galaxies has been a key aim in observational cosmology for many years. The distance to astronomical objects is calculated using redshift, expressed as the letter z. This is, of course, a time-dependent distortion and is, as a result, measured via redshifting. How much the wavelength of light has been stretched by the expansion of the universe between when light was emitted by the source and when it was observed. Light from a galaxy with redshift z equals 1 has been stretched by a factor of 2 in all wavelengths. A galaxy at z equals 2, for example, has had its wavelengths stretched by a factor of 3. The redshift distance relation depends on the expansion history of the universe, which depends on the universe contents. The currently known highest redshift galaxies have redshifts greater than z equals 10. At z equals 10, the universe is observed to have expanded just by a factor of 11 from when the light was emitted. These galaxies formed when the universe was only 480 million years old, or roughly 3.5% of its present age. The light we see from them has been traveling for more than 13.3 billion years, although their comoving distance is much larger due to the expansion of the universe. So to find galaxies at such extreme redshifts, you need infrared telescopes. When Z increases, light originally emitted at ultraviolet and optical wavelengths is redshifted to the infrared. By the time the redshift is Z equals 10, optical light is redshifted into the near infrared at 1 to 2 micrometers. Far ultraviolet light has now been redshifted into the optical. To detect these galaxies, instruments need to be infrared sensitive, and the atmosphere must be transparent to the relevant wavelengths. That's usually space-based observatories. Near-infrared and optical Hubble Space Telescope UDF-1, while a primarily optical telescope has near-infrared capability that enabled it to detect galaxies as far as Z11. Its deep field observations opened at seemingly blank patches of sky for days, weeks, disclosed thousands of faint, distant galaxies. From each deep field image, you can pick out galaxies representing a broad sweep of cosmic history, from nearby galaxies a few billion light years away to galaxies as they were a couple billion years after the Big Bang. The James Webb Space Telescope, launched in December 2021, science operations starting 2022, was specifically designed to make infrared observation. The JWST's primary mirror is 6.5 meters across, almost 3 times the width of Hubble's, and the infrared instruments aboard it are far more sensitive than those carried by Hubble. JWST is shedding light on the universe's earliest days. From its first months of operation, JWST had identified a cornucopia of galaxy candidates at redshifts above Z equals 10, with some preliminary identifications going as high as Z equals 15 or even farther. One galaxy, observed by JWST, labeled JADES GS Z13-0, exhibited a redshift of 13.2, at an era only 325 million years following the Big Bang. Another candidate was found to have a redshift close to 16, though identifying this candidate spectroscopically was a must. It was as if these discoveries pushed the observational frontier back to the formation of the first galaxies, back to that epoch when starlight first shone on the cosmos. Spectroscopic verification yields unambiguous redshift values. Photometric redshifts, based on how bright an object is in different filters, can be ambiguous, more so in the case of extremely distant galaxies where peculiar spectral features or dust obscuration can confound the analysis. Spectroscopy separates light into different colors or wavelengths, allowing specific emission or absorption lines related to elements in the galaxy to appear. These lines have known rest wavelengths that are measured in laboratories. The difference in observed and rest wavelengths directly measures the redshift, and with very little ambiguity. JWST has spectrographs that can obtain redshifts of even very faint, very distant galaxies. Preliminary results showed that a significant fraction of photometric candidates were indeed at the high redshifts originally suggested. Some were close companions masquerading as distant galaxies because of peculiar properties. This is why you need spectroscopic follow-up for your most extreme claims. The galaxies found by JWST at Z greater than 10, by contrast, appear surprisingly bright and massive for such early times. Many appear to have stellar masses as high as several hundred million or even a few billion solar masses. It poses a problem for galaxy formation theory. Standard theory predicts that the first galaxies to form would be pretty small and faint, building up over billions of years with mergers and by forming more stars. The detection of bright, massive galaxies so soon after the Big Bang also means that early galaxy formation was more efficient than models predicted. They also indicated that a large fraction of the first galaxies are composed of elements heavier than hydrogen and helium. Astronomers refer to these heavier elements as metals, but the term encompasses non-metals elements such as carbon and pushed oxygen. Metals are formed by stars through nuclear fusion. The fact that they are found in early galaxies means that earlier generations of stars must have existed, lived, and died, polluting the gas from which the observed galaxies formed. This moves the era of first stars formation to an earlier period, perhaps just 100 to 200 million years after the Big Bang. Quasars are yet another type of very distant object. These active galactic nuclei are powered by supermassive black holes, usually billions of times more massive than the Sun. Material spiraling into these black holes creates an accretion disk that reaches millions of degrees and generates enormous energy at all wavelengths of light. The most luminous quasars can shine 1,000 times or more as brightly as their entire host galaxy. The overwhelming brightness of quasars also makes them visible at very large distances. Quasars are known to the most distant have redshifts of about z equals 7.5 to 7.6. A quasar known as J0313-1806 has a black hole mass of about 1.6 billion solar masses, yet is seen when the universe was only 670 million years old. This is a big mystery. How did billion solar mass black holes come to be so early? Current theories of black hole formation via gas accretion have difficulty producing objects this massive in this amount of time. Black holes increase their mass by eating matter synthesizing in their environment, but the process is not without limits in speed. The Eddington rate is the rate at which the radiation force from the inward flow of matter balances gravitational attraction. A black hole can grow exponentially when it is accreting at the Eddington rate, with an E-folding timescale of 50 mir. Beginning with a stellar mass whole 10 to 100 solar masses, and allowing constant Eddington limited accretion over 700 million years yields a hole of maybe a few hundred million solar masses, still well below the observed billion solar mass sources. Many solutions have been proposed. Maybe the first black holes actually formed by the direct collapse of huge gas clouds, instead of by the collapse of stars, resulting in larger seeds that had more time to develop into billion solar mass black holes. Maybe accretion was done at super Eddington rates in the early universe because things were different. Or maybe the black holes underwent short-lived bursts of extreme growth during galaxy mergers. None of these lines of reasoning is entirely satisfactory, and the formation of billion solar mass black holes at z greater than 7 is still an open question in astrophysics. Quasars are also probes of the intergalactic medium, the tenuous gas that occupies the space between galaxies. As the light of a distant quasar makes its way towards us, it intersects with clouds of hydrogen. These clouds absorb light at a specific wavelength corresponding to the Lyman alpha transition of hydrogen and create absorption lines in the spectrum of the quasar. Different clouds at different distances generate a set of absorption lines at different observed wavelengths, what astronomers call the Lyman alpha forest. The Lyman alpha forest contains information about the distribution and nature of intergalactic gas across cosmic history. In the forest of low redshift nearby quasars are many sharp lines, which is evidence the intergalactic medium is highly ionized. At high redshift, z greater than 6, the forest becomes increasingly absorbed and is ultimately completely obscured at L greater than LBOBS. This Gunn-Peterson trough suggests that the intergalactic medium was still partially neutral at these early times. Meanwhile, the universe was going through reionization, during which time ultraviolet radiation from the first stars and galaxies ionized the neutral hydrogen that had existed since recombination. The reionization era is somewhat akin to a second phase change in the universe. Neutral hydrogen atoms filled the universe after recombination at about 380,000 years. This neutral gas absorbed ultraviolet radiation, so the universe was opaque to these radiations. The first stars and galaxies were forming and providing a source of ultraviolet radiation to ionize the surrounding neutral hydrogen gas, which originally was creating bubbles of ionized gas. As these bubbles expanded and merged over time as more stars formed, they continued to grow. Eventually, the bubbles overlapped and the entire intergalactic medium was again ionized in the era of reionization. High redshift quasars and galaxies indicate reionization was nearing completion by z equals 6, about 1 billion years after the Big Bang. But it took a long time. It began likely at z equals 15 or higher and proceeded slowly over several hundred million years. Regions of space were reionized at different times depending on their concentration of star-forming galaxies. Not all parts of the universe were the same at any given time in reionization. When reionization occurred and the details surrounding it are still not entirely known, partly because the observations required are so difficult. Observations of the JWST are at the forefront of defining the science of reionization. Astronomers can then determine whether those early galaxies made enough ionizing photons to reionize the universe by finding galaxies at z greater than 10, measuring their ultraviolet luminosity. Early results indicate faint galaxies, too faint for Hubble to see, but well within the reach of JWST, may have contributed a substantial portion of the ionizing radiation. These galaxies were much more common than the rare luminous galaxies, and so their combined effect might have been the dominant contributor to reionization. Gamma-ray bursts are also a category of extremely distant objects. Such powerful bursts of gamma rays can last anywhere from milliseconds to minutes, making them the highest energy events known in the universe. Long-duration gamma-ray bursts, those with a duration greater than about 2 seconds, are associated with the deaths of massive stars. A rapidly rotating, very massive star collapsing to a black hole may generate jets of relativistic particles that break through the stellar envelope and emit strong gamma-ray beams. The furthest gamma-ray burst confirmed spectroscopically is GRB 090423, which lies at z equals 8.2. This corresponds to roughly 630 million years after the Big Bang. The burst was located by the Swift satellite, and its infrared afterglow was detected by telescopes on the ground. Study of the afterglow spectrum confirmed the high redshift and was able to deduce properties of the star-forming region in which the burst took place. Gamma-ray bursts provide a unique probe in the high redshift universe. Instead of exposure times of hours for galaxies, gamma-ray bursts briefly become bright enough to detect them one at a time, even at extreme distances. Their afterglows are accessible to detailed study and can be used to place constraints on the stellar populations and gas content of very early galaxies. There is good reason to believe that even higher redshift gamma-ray bursts have happened that weren't recognized as such as their gamma rays were redshifted into X-rays, or even into ultraviolet bands. There's fat that separates these disjointed objects like galaxies and quasars from the smooth CMB, the epoch of the first stars. These objects, known as population 3 stars to astronomers, have never been directly seen. As with all star populations, the terminology is a misnomer. Population I is the youngest and has the highest metallicity. Population 2 is older, and population 3 wood is the earliest and would be essentially metal-free. Population 3 stars would have formed from gas composed almost entirely of hydrogen and helium, the elements made in the Big Bang. With no heavier elements to provide coolant and radiate away its heat, the gas clouds from which these stars emerged would have stayed rather warm, where possibly the progenitor of the solar system was born. These enormous original stars would have burned hot, albeit rapidly, depleting their nuclear fuel within a handful of million years. Population 3 stars would have exploded as supernovae or collapsed directly into black holes when they ended their lives, depending on their mass. They would produce heavier elements in a supernova and seed the surrounding gas with those elements, enriching the gas that forms the next generation of stars. These black holes may have also acted as seeds for the supermassive black holes powering distant quasars. Direct detection of population 3 stars is still one of the key goals of observational cosmology. If population 3 stars are sufficiently massive, JWST might be able to detect individual population 3 stars, and if the supernova explosions of these stars can be observed at high redshift. The stars, though, could reveal themselves through their combined impact on the spectra of a very distant galaxy. Some JWST-JADES observations show tentative evidence of strange spectral features that might be interpreted as extremely metal-poor stellar populations, which would be consistent with population 3, but no secure detections so far. The period during which population 3 stars formed, presumably some 100 to 300 million years after the Big Bang, is the cosmic dawn, marking the emergence of starlight in what had been a dark universe filled with neutral hydrogen. This era is just tantalizingly close to current observations. JWST observations at Z equals 15 to May 20th be able to look back to the cosmic dawn itself. Although identifying population 3 from later, metal-enriched populations involves considerable difficulties. Even before population 3 stars is an era that cosmologists call the Dark Ages. This era, extending from recombination at 380,000 years to the formation of the first stars perhaps 100 million years later, was one in the universe had matter but no luminous bodies. Neutral hydrogen stood in the way of stars, but no stars shined yet. Galaxies were just concentrations of dark matter, holding onto gas, but not yet forming stars in the gas they were containing. This age is known as the Dark Ages, not because it was in darkness, there was no one living to see darkness or light, but because there was no production of electromagnetic radiation we could observe then and here. The Dark Ages are an observational desert. There weren't any stars or galaxies to light them up. The CMB had already been emitted at recombination. No electromagnetic signal from this era can arrive to us since nothing was seen at such a time emitting any signals such as that. The only possible probe of the Dark Ages lies in observations of neutral hydrogen itself. Hydrogen in its ground state emits a spectral line at wavelength 21 centimeters related to a transition involving spin state of its electron. This line is observed routinely in nearby galaxies to map the distribution of neutral hydrogen gas. In the early universe, the 21 centimeters line is redshifted to much longer wavelengths. Emission or absorption from dark ages should be observed today at the radio wavelengths on the order of a few meters. Several projects are attempting to detect this signal. Among these LOFAR in Europe, the Murchison Wide Field Array in Australia, and the Square Kilometre Array, which is yet to be built. These are instruments that seek to discern the weak 21 centimeter signal beneath the glare of emission from our own Milky Way and other extragalactic radio sources. The requirements are staggering and no positive detection has yet been reported, but the potential scientific payoff makes it worthwhile. Observation of the 21 centimeter signal from Dark Ages cosmic dress would thus deliver us new information about the temperature and degree of ionization of the intergalactic medium, the formation of the first stars, and the onset of reionization, none of which is obtainable with any other cosmological probe. It also would add a vital missing chapter to cosmic history, linking the smooth, uniform universe revealed by the CMB to the lumpy, galaxy-filled cosmos we see today. When we look back even further in time, to times prior to recombination, we find events which can be investigated only by non-electromagnetic means if they can be investigated at all. The neutrino decoupling 1 second after the Big Bang produced the cosmic neutrino background, not yet detectable, but theoretically accessible with sufficiently advanced technology. The gravitational wave background from inflation may be observed in the imprint it leaves on CMB polarization or with future space-based gravitational wave detectors such as LISA. But there is an absolute limit, beyond which no observation is possible even in principle. It is the cosmological horizon, set by the finite age of the universe combined with the finite speed of light. No phenomenon is able to send signal to us from a place where the light travel time is larger than the age of the universe. To be precise, no signal can arrive from beyond the particle horizon, which is defined relative to the expanding universe, and this is the boundary of the observable universe. The particle horizon is at a comoving distance of about 46.5 billion light-years. This is the distance to the most distant objects which signal could have reached us from since the Big Bang. No object at any distance away has sent signals to us yet. Its light is still on the way and has not yet arrived. Such objects may exist. There is no reason to believe the universe ends at the particle horizon, but they are in principle unobservable to us right now. The particle horizon is increasing with time. Over time, as the universe gets older, light has had the time to travel to us from ever more distant regions of space. The observable universe is growing, but not because of the motion of objects, but rather because of the passage of time, which allows light to travel further. In a universe of constant or decelerating expansion, the particle horizon would grow to contain everything in an infinite amount of time. They said, all would be observable in time if only its light had time to reach us. But our universe is not constant or decelerating in its expansion. It is expanding at an accelerating rate, driven by dark energy. This acceleration introduces a nuisance called the cosmological event horizon. This horizon is at a comoving distance of some 16 to 17 billion light-years, and it defines the furthest edges from which we will ever be able to receive signals. Because of accelerating expansion, objects out past the event horizon are receding from us so fast that their light will never reach us, even in eternity. The event horizon is shrinking like a black hole. Conclusions that currently are certainly just a few regions in the event horizon can be observed in principle, since they will still be a larger year all the way until the end of time, as acceleration takes them out to the speed of light faster than light can catch them. On timescales of the order of 100 billion years, all but a few of the galaxies we now observe will recede outside of our event horizon. Future observers will look out on a far emptier universe and see their local group of gravitationally bound galaxies as the only ones still within view. It has profound implications, said Professor of Astronomy and Chair of the Department. Cosmoants trillions of years from now will look out on a cosmos whose only point of light is their local galaxy. Other galaxies will have receded beyond the event horizon. So the CMB will be redshifted to really long wavelengths, and by then you cannot detect it. All evidence for the Big Bang, for the expansion of space, for the existence of other galaxies will have been swept away. Fathered by access to infinite amounts of data, these future observers may concoct completely different cosmological theories founded on the scan observation. But we live in a time when the universe is very forthcoming about its history. We can study galaxies that are billions of light years away. We can observe the CMB from almost 14 billion years ago. We can also use it to measure cosmic expansion, and this tells us the age and composition of the universe. We occupy a unique period in time when cosmology is attainable, when the universe has existed long enough to form structure and complexity, but has not been stretched so far that all traces of cosmic history have been removed from observational horizons. The farthest we can see depends on what it means to see. In electromagnetic radiation, the CMB marks the ultimate limit, coming from a comoving distance of 46 billion light-years, when the universe was 380,000 years old. Individual objects such as galaxies and quasars have been detected to redshifts greater than z equals 13, which corresponds to more than 13.4 billion years of light travel time and about 33 billion light-years in comoving distance. But if we broaden our definition of particles to include more than just photons, Then the cosmic neutrino background brings us back to 1 second after the Big Bang, though it remains undetected. If we consider gravitational waves, primordial signals from inflation may in principle allow us to directly probe the very first tiny fraction of a second, although, once again, no such signals have been detected. The ultimate theoretical limit is the particle horizon at 46.5 billion light-years, the edge of the observable universe. Additional to this space-time that exists but has not yet contacted us. Outside the event horizon at a distance of 16 to 17 billion light-years, there is space that will never reach out to us, dragged away by unrelenting acceleration before any signal could cross the widening chasm. These distances aren't just big, they are cosmological big, on the scale of the universe itself. They're not just spatial differences, but temporal ones. They are peaks into times when the universe was young, hot, and by implication radically unlike today. When we look at the CMB, we're seeing the universe as it was when it first became transparent, this warm fog of hydrogen atoms at 3000 Kelvin. When we look at high redshift galaxies, we see the very first structures forming, the first stars burning, the first metals being made. The universe's history plays out before us, written in light that has journeyed for billions of years. Any observation of a distant object is at the same time an observation of the distant past. Astronomy is unique among sciences in having a direct window into history. A biologist cannot directly observe dinosaurs. A geologist can't watch mountain ranges grow in real time. But an astronomer can actually look back in time and see the early universe, see galaxies being born, see cosmic evolution playing out. This window on history is a consequence of the finite speed of light and the vastness of the cosmos. In our lives, light feels instantaneous. The pause between throwing the switch and seeing the light is imperceptible. But light speed is painfully slow on cosmic scales. Light takes years to traverse the distances to nearby stars, millions of years to travel to distant galaxies, and billions of years to come from the time of the CMB. That light which now meets your eye from the extreme reaches of the observable universe began its journey before the Earth existed, before the Sun was born, even before our galaxy took on its present form. That light propagated through expanding space for almost the entire age of the universe. It has witnessed cosmic history from within, crossing epochs of exponential expansion, formation of structures, and galaxies' evolution. Encoded in its wavelength and strength is information about a long-ago environment. Every photon is a messenger out of time. The oldest photons we can observe, those of the CMB, are also the oldest things we can see. They are more ancient than any star, any galaxy, any assembly in the universe. They were formed when the cosmos itself was younger than now a human embryo, when all the matter that would one day make galaxies was squashed into a largely homogeneous, ballooning fireball. How far away is the furthest thing we can see is really a question of time as well as space. The farthest are also the oldest. The CMB is 46 billion light-years away in comoving distance, but also 13.8 billion years ago in time. They are not two things that we can pull apart. Distance and time are linked in cosmology. They are two sides of the same space-time interval. This link between the parts and the whole gives cosmology its special flavor. We're not looking at the universe as it is, but as it was. Our probes sample various cosmic epochs as a function of distance. Distant galaxies show us the recent universe. Distant galaxies show us the young universe. The CMB is the baby universe. We do not see cosmic evolution as evolution over time of a single object. We see it as the different ages of a lot of different objects at different distances, literally different epochs of cosmic history. You could argue that this is cosmic archaeology. Just as archaeologists piece together human history by studying artifacts from different time periods, cosmologists piece together cosmic history by studying objects at different redshifts. A galaxy at z=1 represents a time when the universe was roughly half its current age. A galaxy at z=2 represents a time when the universe was some 3 billion years old. The sequence extends back into cosmic history, each redshift layer capturing a moment in time of the universe. Observations at multiple redshifts have enabled cosmologists to narrate the story of star formation, galaxy evolution, chemical enrichment, and large-scale structure evolution. This past reconstruction shows that the universe is not the same now as it was then. The star formation rate peaked around z=2 to 3, some 10 to 11 gigayears ago. The past was full of compact, gas-rich galaxies. The intergalactic medium was gradually enriched with metals as successive generations of stars were born and died. The large-scale structure became more prominent because gravity boosted the initial density perturbations. We live in a universe that is old enough to be considered mature, having evolved for almost 14 billion years. The first billion years of that process of evolution are just now coming into focus through JWST observations. Even the very earliest times, the first few 100,000 years or so, are available through the CMB. Between these bookends is the entire range of cosmic history, a narrative told in light from across space-time. The most distant object we can see is the CMB, which is coming from the surface of the last scattering at a comoving distance of about 46 billion light-years. But that answer, while accurate, misses something of the awe and depth of the question. We're not just looking at an object, we're looking at an object that is so far away. We're looking at the universe itself as a baby, seeing what conditions were like when all the stuff that would eventually become stars and galaxies and planets was crammed into a boiling hot, thick fog of plasma. We are looking at light that was emitted before the first stars lit up, before the first galaxies formed, before any of the structures we see in the contemporary universe existed. We're looking at the building blocks from which everything was built, the primordial matter from tiny density ripples like these that grew into a cosmic web of clusters and voids. We are looking as far as photons can allow us, back to the time when the universe became transparent and light could at last travel unimpeded across cosmic distances. This is the farthest thing we can see. Not a galaxy, not a star, not any tangible thing, but the universe itself, showing us its earliest moment that we can observe. After that, it's the Dark Ages, the age of first stars, and then eventually the Big Bang, obscured behind the impenetrable plasma of the first 380,000 years. Electromagnetic radiation can't be used to see beyond the CMB, because before the CMB there was nothing to see. The universe was opaque. Light could not propagate. It was not even possible to see. But this is a fundamental limit, not a technological one. Even an idealized telescope with perfect optics and an infinite number of pixels, a pixel size of 0 arcseconds squared, basically. I know, this is a very hypothetical concept, not physically possible. Could not look further back in time than the CMB and photons. The information is just not there to be sensed. The universe has given us a present in the form of the CMB, a direct view of the cosmos at 380,000 years old. And it also imposed a bound. We can't look any further back using light. Hold on the baby, he said. But nearly the entire history of the universe is contained within that bound. From 380,000 years to 13.8 billion years, from the CMB to today, we watch cosmic evolution in action. We witness galaxies being born, expanding, colliding. We see stars turn on and off. We watch the universe expand, space stretch, and structure form. We can piece together the history of all there is to know and track it all back to what were, are and might always be the first moments we can see. What is the distance from which we can receive light? In moving distance, 46 billion light years. The farthest is 18 miles in depth. Best distance is 18 miles. In moving distance, the furthest we can see is about 46 billion light years away. In light travel time, it is about 13.8 billion years away, and the cosmic age of that light is exactly 380,000 years when that light was emitted. These are really the figures that describe the size of the observable universe and the amount of cosmic history you're looking at, and the extreme limit of what you can see through the opaque early universe. Beyond this, there are spaces which we cannot see and times which we cannot look upon, and perhaps there are infinite worlds such as ours which we cannot know. The universe might be substantially larger than the part we can see. Even if the universe potentially contains regions that remain forever invisible to us, galaxies that we will never see, and even regions with different physical constants. But only light that meets us can be left behind, and light can meet us only in the finite sphere defined by the particle horizon. That area, that crust of the observable universe, has enough marvels to keep stargazers busy over eons. 2 trillion galaxies, each containing hundreds of billions of stars. Unlimited planets, many livable. Supermassive black holes, neutron stars, quasars, gamma-ray bursts, supernovae, filaments, and voids on large scales. The CMB, with its tiny temperature fluctuations that encode the seeds of all structure. Dark matter, dark energy, the whole cosmic web. It is all within the observable universe, all within the radius of our past light cone. The outermost boundary of this region, known as the CMB, is the deepest look back in cosmic time that we can obtain using photons. It is the oldest light, the most ancient signal, the deepest thing we can see. And with it we see the universe as it once was, aglow in the backwash of creation, 380,000 years after the origin of all. In order to place the scale of what we can see in perspective, we first need to understand what these distances mean in practical terms. When astronomers tell you the CMB comes from 46 billion light years away, they're talking about a distance so mind-bogglingly huge that no human mind can really comprehend it. Let's try to get a feel for the scale by making a few comparisons one after another. Earth is about 150 million kilometers away from the Sun on average. This distance is known as 1 astronomical unit and acts as our baseline cosmic ruler. Light travels that distance in 8 minutes and 20 seconds. When you look at the Sun, you don't see it as it is right now. You see it as it was 8.5 minutes ago. If the Sun disappeared, we wouldn't know for more than 8 minutes. The last light it gave off would keep on traveling toward us, giving the illusion of a sun that no longer is. Farthest major planet in our solar system, Neptune, orbits the Sun at about 30 astronomical units. Light takes approximately 4 hours to travel from the Sun to Neptune. A message transmitted to a spacecraft at Neptune would require 4 hours to reach it and 4 hours for any reply to get back. The round-trip communication time is 8 hours. That's the scale of our immediate solar system neighborhood. The Oort cloud, a spherical shell of ice and rock defining the actual boundary of the Sun's gravitational reach, is believed to stretch out to around 100,000 astronomical units. The inner boundary of the Oort cloud is reached by light in 1.6 years, and the outer boundary, perhaps in 3 years. This is the real extent of our solar system, the full 9/10 of a light-year stretch. Now Alpha Centauri is the closest star system at 4.37 light-years away. This is about 276,000 Australian dollars, or 2,760 times the distance to the inner edge of the Oort cloud. The signal for a visit to Alpha Centauri is delayed by 4.37 years. You will have to wait for 4.37 more years for answers. Communication takes 8.74 years for round trip. This is interstellar space, the distance between the stars. Our cosmic home, the Milky Way, is about 100,000 light-years across. It says we live about 26,000 light-years away from the galactic center. The central region emits light 26,000 light-years to long ago, so that we see the galactic center as it was 26,000 years ago before human history was recorded. Light coming from the opposite side of our galaxy, about 100,000 light-years away, allows us to see that part of the galaxy as it was 100,000 years in the past, before Homo sapiens had even left Africa. About 2.5 million light-years away is Andromeda, our closest large galactic neighbor. That's 25 times the diameter of the Milky Way. 2.5 million years ago, we left the primitive hominid so close to other great apes, if not indistinguishable. Every star, every gas cloud, every dust cloud, everything we can see in Andromeda is showing us the universe as it was in that bygone day and age. The Virgo cluster is a giant blind of galaxies with more than 1,300 member galaxies at a distance of 54 million light-years. This is over 20 times the distance to Andromeda. The light we get from the galaxies of the Virgo cluster was emitted pre-asteroid impact that killed the dinos, pre-mammalian aficionados of their current shapes, pre-grasses sapling the continents. We see these galaxies as they were in a time on Earth so different from our own world. JWST has observed the most distant galaxies to date left approximately 13.4 billion light-years away in light travel time. Through repeated comparisons, this distance is so far beyond the comprehension. It is about 250 times farther than Virgo. It is 5,360 times farther than the distance to Andromeda. It is larger than the size of our galaxy, multiplied by 134,000. No amount of comparativeness can make such distances even remotely intuitive because they are so far removed from human experience that our minds simply cannot interpret them in any meaningful way. Yet even these most distant galaxies lie substantially closer than the CMB. The comoving distance to the CMB itself, with cosmic expansion taken into account, is about 46 billion light-years. This is larger than the distance to the farthest galaxies by almost a factor of 3.4. It represents an absolute boundary in the observable universe, a limit beyond which no signal could have reached us. In order to understand what 46 billion light-years means, realize that this distance in kilometers has 26 digits. The number when written out is 435 septillion kilometers. The human mind cannot grasp such things. We can apply mathematical operations to them, but we cannot see them or keep them in mind as we keep an image of a far-off mountain or even an image of the moon. This is the scale of the universe. Our world, our solar system, even our galaxy are just minuscule specks in the observable universe. The Milky Way has hundreds of billions of stars and is 100,000 light-years across, but it is less than 1/4% of the distance to the CMB. All the stars that we can see in the night sky, thousands visible to the naked eye, are within a few hundred light-years. This is some 10.6% of the observable universe. We reside in a cosmos so grand that it defies all attempts to convey its scale to our everyday experience. The sky we see, packed with stars, is just a tiny fraction of local space. Outside is vastly more universe we cannot see with the naked eye. Telescopes enhance our sight, bringing galaxies by the billions into view, structures on the scale of millions and billions of light-years, and finally the CMB itself. The narrative of how humanity became aware of this scale is one of the great intellectual accomplishments of our species. The shape and size of the universe were unknowable for the vast majority of human history. Stars had been recognized as distant in ancient times, but there was no way to gauge how distant. Built in the early 1600s, the telescope showed that the universe was not what the naked eye revealed it to be, but failed to provide distance determinations to the bulk of objects. The progress was made in the early 20th century when astronomers learned how to measure distances in space. The insight was to find standard candles. Things this bright is known. When the known intrinsic brightness is compared with the observed apparent brightness, the distance can be derived by the astronomers. The relation is an inverse square law. When an object is twice as far away, it looks 4 times dimmer. It looks 100 times dimmer when an object is 10 times farther. If one measures the apparent brightness and knows the intrinsic brightness, one can calculate the distance. Cepheid variables provided the first reliable standard candles and was the workhorse of the first distance scale. These stars have pulsation periods that depend on their intrinsic luminosity. Brighter Cepheids pulsate more slowly. Dimmer ones pulsate faster. By determining the pulsation period, the astronomers can get the absolute luminosity. Based on the observed apparent brightness, they infer the distance. Henrietta Swan Leavitt found this relation in 1908 among Cepheid variables in the Small Magellanic Cloud. In the 1920s, Edwin Hubble applied that information to Cepheid variables to measure the distance to Andromeda and other nearby galaxies, showing for the first time that these nebular objects were truly island universes well beyond the Milky Way. This discovery revolutionized our concept of the size of the universe. What had seemed to be a cosmos with one galaxy, the Milky Way, and maybe a few fuzzy nebulae of uncertain nature was revealed to be a universe full of distinct galaxies, each as substantial as the Milky Way and separated from each other by millions of light years. But Hubble did more. He measured the distances to dozens of galaxies and found that more distant galaxies appeared to be moving away from us at faster speeds, redshifting toward longer wavelengths in the spectrum due to the Doppler effect. This redshift, as astronomers call the effect, obeys a simple law. Velocity is proportional to distance. Galaxies twice as far away are receding twice as fast. This proportionality, now called Hubble's law, was the first indication that the universe is expanding. Expansion of the cosmos puzzled a lot of people in the beginning. It sounds like galaxies are flying through space, traveling away from one another as shards from a blast. But this line of thinking is wrong. The galaxies are not in motion in space. The space is expanding, and with it the galaxies. The difference is a bit subtle, but very important. Imagine placing dots on a balloon and then blowing it up. The dots spread off from each other, but not because they are moving on the surface of the balloon. They separate because the surface itself is expanding. Every dot moves away from every other dot. An observer at any dot sees all the other dots moving away from it, and with the further dots moving away faster. This is precisely what we find in the universe. Regardless of which galaxy we look from, all the distant galaxies are receding and their recession velocity is proportional to distance. Since this means that galaxies that we see at very large distances are moving away from us at very high speeds. Galaxies at redshift z equals 1 recede at about 60% of the speed of light. Galaxies at redshift z equals 2 recede at around 80% of the speed of light. At even larger redshifts, the recession velocity, the rate of change of the comoving distance, is larger than the speed of light. Recession velocity is not real motion through space, but instead space itself expanding between objects of matter, so it does not violate relativity. The CMB itself is at a redshift of about z 1100. That is to say, the universe has expanded 1,100 times since the CMB was radiated. This factor stretched wavelengths of light and nobody of galaxies. The CMB was emitted as light and infrared radiation from 3000-degree material. Expansion has stretched these wavelengths by a factor of 1100. turning light into microwave radiation at a temperature of 2.725 Kelvin. This stretching of wavelengths is a direct measure of cosmic expansion. In fact, every single photon in the CMB has seen its wavelength stretched by a factor of 1100 on its way from the surface of last scattering to detectors today. But this is not a Doppler shift in the classical way. It is a cosmological redshift due to the expansion of space itself. As space expands, the photon's wavelength is stretched so that the number of wavelengths across an expanding space remains constant. Expanding on this is key to understanding why the CMB is from 46 billion light-years away, even though it's only 13.8 billion years old. The comoving distance to the surface of last scattering includes all of the expansion that took place while the photon was in transit. The line-of-sight region which emitted the CMB photons which we detect today was at an effective comoving radial distance of just about 42 mpc when the photons left that region. But over their 13.8 billion-year voyage, space grew 1,100 times. This dilation carried the emitting region out to its present-day comoving radius of 46 billion light-years. Varying cosmological models lead to different relations for redshift distance based on the expansion history. The precise relation depends on the amount of matter, radiation, and dark energy at various cosmic times. In the early universe, radiation dominated the energy density and the expansion was rapid. Matter came to dominate later, and expansion slowed. And lastly, dark energy became dominant, making the expansion accelerate. The effect of this evolving expansion history means that redshift is not equivalent to distance simply because it is associated with a Doppler shift. AZ equals 1 galaxy is not half as far as AZ equals 2 galaxy. The actual distances are a function of the entire expansion history. Computing comoving distances involves choosing a cosmological model and its parameters, e.g., the Hubble constant, the matter density, and the dark energy density. Various parameters will give a slightly different distance even at the same redshift. These parameters have been measured to incredible precision from independent observations by modern cosmology. The constraints are strongest from the CMB. The pattern of hot and cold spots in the CMB temperature map is highly sensitive to cosmological parameters. The scale of the spots, the magnitude of temperature fluctuations, and the shape of the statistical distribution all contain information about the contents and geometry of the universe. The Planck satellite observed CMB temperature and polarization over the full sky with unprecedented accuracy. Planck data analysis provided cosmological parameters with errors of just 1 or 2%. The Hubble constant was measured to be 67.4 kilometers per second per megaparsec, prior uncertainty of approximately 0.5%. The total matter density was found to be 31.5% of the critical density. The density of dark energy was 68.5%. The spatial curvature was limited to be very close to zero, indicating the universe is spatially flat, so that the distance can be calculated precisely to any redshift. They convert redshift, which we observe directly from spectra, into distance, which we cannot observe directly. They give us confidence to say that CMB is from 46 billion light-years away. Galaxies at z equals 10 should be approximately 32 billion light-years away, and that the observable universe is 46.5 billion light-years in radius. The accuracy of today's cosmology is a truly astounding thing. The size and age of the universe were uncertain by factors of 10 or more a century ago. Various astronomers had suggested ages of anywhere from millions to trillions of years. Distance estimates varied by comparable factors. Today we know the age to within 20 million years out of 13.8 billion. We understand the size of the observable universe to within a few percent. This transition from ignorance to precision was enabled by a combination of theoretical developments, most notably general relativity and quantum mechanics, and observational revolutions, especially the discovery of the CMB and the observation of distant supernovae. The CMB alone is jam-packed with information about more than just the confirmation of the Big Bang model. The slight fluctuations in temperature across the sky, measured to be on the order of 1 part in 100,000, contain information about the initial density variations that eventually formed galaxies and clusters. These perturbations were generated during inflation, an era of exponential expansion that took place in the earliest fraction of a second after the Big Bang. Inflation theory, first proposed by Alan Guth in 1980 and subsequently refined by many others, holds that the universe experienced a brief interval of exponentially rapid expansion driven by a scalar field known as the inflaton. During this expansion, tiny variations in the inflaton field at the quantum level were magnified to astronomical scales, producing the matter density fluctuations we detect in the CMB. They had a nearly scale-invariant spectrum, i.e., the perturbations had the same amplitude at all length scales, precisely the pattern that we see in the CMB. The accurate predictions of observed CMB features made by inflation provide strong evidence in support of the theory, although direct evidence has not been found. The expected primordial gravitational waves would be conclusive, but have not yet been detected. Several experiments have made tentative detections that were later shown to be foreground contamination from dust in our own galaxy. The hunt continues with more powerful eyes. The CMB fluctuations contain information about the composition of the universe as well. The relative amplitudes of hot and cold peaks on different angular scales in the power spectrum are governed by the relative amounts of ordinary matter, dark matter, radiation, and dark energy. Dark matter, which interacts gravitationally but not electromagnetically, influences the rate at which density perturbations grow. More dark matter results in larger fluctuations. The observed pattern demands about 27% of the energy density in the form of dark matter. The nature of the dark matter is unknown despite decades of searches. It is not normal atom-based matter, which has own characteristic absorption and emission lines spectroscopically. It is not antimatter, which would annihilate with matter and generate gamma rays that we could detect. It is not primordial black holes, which would also create gravitational lensing signatures that can be detected. The leading candidate scenario is that dark matter is made out of weakly interacting massive particles, or WIMPs, produced in the early universe and still around now. Even though they have been subjected to stringent searches in underground detectors, particle accelerators, and astrophysical observations, WIMPs have not been conclusively detected. Other theories include axions, sterile neutrinos, or other exotic particles beyond the standard model. Some people even doubt whether dark matter actually exists, and instead propose that we need a new theory of gravity. But the evidence for dark matter from several unrelated experiments is very compelling. 27% of the energy density of the universe is something that allows us to feel its gravitational pull, which we see is what shaped the development of the cosmic web of structure, but that doesn't interact with us electromagnetically. Dark energy is an even greater mystery. Introduced in 1998 through observations of distant-type Ia supernovae, dark energy is understood to drive the accelerating expansion of the universe. The supernovae were dimmer than expected, suggesting that they were farther away than their redshifts would imply in a decelerating universe. This unexpected finding, corroborated by several other studies, implies the rate of expansion has been increasing over the last few billion years. Dark energy acts like a cosmological constant, a fundamental feature of empty space, in the sense that it has constant energy density, even as space expands. The universe is expanding as more space is created, and more dark energy is created. This drives the acceleration of expansion. The nature of the process, called dark energy, is entirely unknown. It might be vacuum energy, the quantum mechanical energy of empty space. It may be a new field, like the inflaton, but alive today. It could be indication that the general relativity has to be modified at cosmological scales. The challenge of figuring out dark energy is one of the biggest problems facing modern physics. Several working groups are trying to better quantify its properties, looking for changes in its density as a function of time or departures from cosmological constant behavior. These observations may tell scientists if dark energy is actually the same constant energy density they have observed so far, or changing in a way that could shed light on what it really is. The fate of the universe is greatly influenced by the presence of dark energy. In the absence of dark energy, the expansion would slow down and perhaps reverse into contraction. When dark energy dominates the universe and it has constant density, the expansion rate accelerates without limit. The universe is expanding, becoming increasingly cold and distant from galaxy clusters. Finally, even gravitationally bound objects like galaxies and clusters of galaxies will be torn apart. This destiny, sometimes known as the Big Rip, may be trillions of years off if it's right. For one thing, dark energy causes observational horizons, walls beyond which we cannot see. The event horizon, which is different from the particle horizon, delineates the farthest regions that could in principle ever send us signals. Even with an unlimited amount of time, we still could not receive light from beyond the event horizon, as space is expanding faster than light can travel. This horizon at present is at about 16 to 17 billion light years, which is yet much closer than the particle horizon at 46 billion light years. That is to say, some of the galaxies we now have in sight will ultimately fall out of sight. They are beyond the event horizon, which means you can never see what they look like right now from Earth. While billions of years ago we do see them, but we will never see them evolve beyond a certain epoch. The light of the later stages will never come in the early universe. Space stretches faster than it can travel. Even further in the future, on the timescale of hundreds of billions of years, your average galaxy will have receded beyond our event horizon. We don't like to think too hard about that one. Observers in the future will view a vastly emptier cosmos, consisting solely of their local gravitationally bound system, perhaps a merged Milky Way Andromeda galaxy and its satellites. Every other galaxy is expected to have vanished beyond the horizon, its light redshifted out of detectability. The CMB will have cooled to such low temperatures that it effectively becomes invisible. A future generation of cosmologists will be confronted with a universe that reveals little of its own past. This is a puzzlingly large cosmological coincidence. We live in an age when cosmology is possible, when the universe lays out its history with challenging abundance, when galaxies swarm the sky and the CMB is still detectable. This window of opportunity opened roughly 10 billion years ago when the buildup of structures became the dominant form of matter and energy in the universe, and it will close perhaps 100 billion years from now when most galaxies have journeyed beyond the horizon. Roughly, intelligent observers before about 3 billion years after the Big Bang would have had almost nothing to see, and intelligent observers after perhaps 100 billion years after the Big Bang will see a universe so empty that it will give them little indication of its real nature. The universe would still be too young for complex structures. Intelligent observers arising later than perhaps 100 billion years after the Big Bang will look out upon a very empty universe that offers very little clue concerning its real nature. We are living in the era when the cosmic history is observable. This realization adds to the poignancy of the question of how far we can see. We can see very, very far, all the way to the edge of the observable universe, to the CMB at 46 billion light-years. But this extraordinary visibility is transient. It won't always be that way. The universe won't always be that revealing. The horizons are closing, gradually but relentlessly, as accelerating expansion moves the distant regions out of our grasp. Every observation of a faraway galaxy, every photon collected from the infant universe, is information that at some point will be unavailable. The record of cosmic archaeology is vanishing, smudged out by expansion that elongates wavelengths to invisibility and transports sources beyond horizons. We live at a time when we can still see much of cosmic history, and that's something we should all be thankful for. The instruments we build, the observations we take, the data we acquire, these are a cosmic legacy that may never be repeatable. JWST images of Z greater than 10 galaxies do show objects with structures that will ultimately be impossible to see. Planck's CMB measurements may be close to the ultimate precision attainable until the signal cools beyond detectability. We are chronicling the universe during its short stretch of maximum observability. This bodes well for upcoming and future astronomical missions. The Nancy Grace Roman Space Telescope, slated to launch in the late 2020s, will cover wide swaths of sky in infrared wavelengths, detecting thousands of high redshift galaxies and probing the nature of dark energy with unparalleled accuracy. It is designed to explore distant galaxies and characterize the atmospheres of exoplanets and other Earth-like planets. For instance, future missions could involve yet larger space telescopes, gravitational wave detectors sensitive to primordial signals, and neutrino observatories that potentially could observe the cosmic neutrino background. Each new capacity either pushes us a bit further in what we can probe into space, or probes new types of signals that complement snapshots of the electromagnetic sky. None of this is to say that these limits, all of these efforts are bronzed in fundamental limit. They are absolutely undergirded in fundamental limits. There is no way to look through the opaque plasma that permeated the universe before recombination. We can't get signals from beyond the particle horizon. We cannot look outside our cosmic light cone, the region of the universe from which information moving at the speed of light could already have reached us. These aren't technological limits that will be overcome by engineering. These are fundamental limits set by the age of the universe and the speed of light. What lies beyond debate the farthest thing we can observe, the CMB from 46 billion light-years away, is not simply something we look at. It is the outermost limit of the knowable universe, beyond which we cannot probe using electromagnetic radiation. Everything that is nearer than the CMB is potentially still observable if you are bright enough or have the right instrument. Everything at the CMB is the oldest light, the oldest seismogram, and the most distant in the electromagnetic spectrum. And all before the CMB forever remains locked behind an opaque veil, viewable only via non-electromagnetic means, if at all, eternally outside the domain of photons. That's as far as we can see. That's the best distance you can see with light-based observation. That is the limit set by cosmic history itself. The CMB at 380,000 years after the Big Bang, at 46 billion light-years away, with a redshift of 1100 and a temperature of 2.725 Kelvin. It is the most distant thing we can see, and it reveals the universe when it was at the time that it first became transparent, shining with primordial light that has journeyed through space for almost the entire age of the cosmos, arriving at our screens as the oldest potential signal, the most distant possible photon, the most remote thing visible in the electromagnet universe. When we think about the most distant thing we can see, we're thinking about more than distance. We are thinking about time, history, and the nature of seeing itself. Every photon contains information about its path home. This is encoded in the wavelength, polarization and travel direction. The photons in the CMB reaching us today have seen almost the whole history of the universe. They left behind matter and radiation when the universe was a hot, dense plasma beyond the surface of last scattering. They propagated through expanding space as that plasma cooled and rarefied, as gravity coalesced matter into lumps, as the universe's first stars were born, as galaxies formed and evolved. These photons lived through the dark ages when there were, as yet, no stars. They observed cosmic dawn, when the first stars lit up and the darkness was dispelled. They watched reionization slowly turn the neutral intergalactic medium back into ionized gas. They have seen galaxies collide, grow and merge, supermassive black holes rise in galactic centers, generations of stars cycling, creating heavier elements and enriching the cosmos. They have seen everything that happened between 380,000 years after the Big Bang and now. But none of this is recorded by the photons themselves. A photon doesn't age while traveling through the vacuum of space. It is emitted with a certain wavelength from the thickness of matter of the emitting material in accordance with the temperature of this matter. As space expands, the wavelength is stretched, but the photon feels no flow of time. In its own reference frame, if one can say such a thing, the trip takes no time at all. It is emitted and reabsorbed at the same time, without any delay. This bizarre characteristic of photons, that they have no time, ties in with even deeper relativity concepts. Anything moving at light speed has zero proper time on its world line. The space-time interval between emission and absorption is null. The path of the photon in the universe is a null geodesic in space-time. That is the path followed by light in the four geometry of the universe. In the photon's rest frame, we, observing on a time-like world line that runs through time, the photon's trip aged 13.8 billion years. The photon is observed to arrive at a long time after its emission originating from some distant ancient source. Yet the photon itself, if it could be said to have experience, left and came in the same moment. This way thinking implies something fundamental regarding the nature of light and information. Information moving at the speed of light traverses space-time intervals, but it doesn't itself experience time. This has implications for how we should think of looking at distant things. When we look at a galaxy at redshift z equals 10, we sometimes say that we are seeing the galaxy as it was 13.2 billion years ago. This is correct in our reference frame. But in the photon's frame, the galaxy is us. It's what we are seeing at the moment we look at it. The space-time distance is zero. Past and present are compressed into a single point at a photon's world line. These considerations touch on philosophical issues concerning the nature of pastness. That distant galaxy, as we see it, still exists, doesn't it? Almost certainly not. The galaxy at z equals 10 that we are seeing has been evolving for 13.2 billion years. It probably merged with other galaxies, spawned fresh generations of stars, and transformed itself. What we see is ancient history. It's all that photons can do, carry information, and freeze frames of what may be rapidly evolving sources. In a way, when we look out into space, we are seeing ghosts, zombies, and skeletons, as one astronomer puts it. The light is real, but the objects might not as we know them be. And supernova at redshift z is observed to us. That's an explosion we're seeing that's 10 billion years old from our point of view. The debris has long since stretched out. Maybe some of that material from stars went into new stars, new planets, new life. The original star is dead, but its light is still heading towards us, and it reaches us today, showing us an event from the distant past. This gap in time observation and reality observation is even more pronounced at distance. Thus, the galaxies we see at the highest redshifts are really looking back in time to when the universe was over 13 billion years younger. Those galaxies have aged 13 billion years since that light left. They may have merged dozens of times. They may have burned through several generations of stars. They could have formed massive black holes, spiral arms, globular clusters, all the trappings of full-fledged galaxies. Or were they obliterated in violent mergers, their stars strewn out across a vast structure that looks nothing like the tiny, irregular galaxy we see in its infancy? We can't see these galaxies as they are now. Their present condition is hidden to us because the light that enables us to see that state has not yet reached us. It won't show up for billions of years if it shows up before going beyond our event horizon. At great distances, we are always only seeing the past of the universe, never the present of the universe. In cosmology, the present is entirely local. Only nearby things can show us their current state, and even nearby means delays of years or millennia for stars and galaxies in our own galactic neighborhood. This is a limitation on what we can learn about the evolution of cosmic structure. We can't observe a single galaxy throughout its evolution from youth to adulthood. The time scale is beyond a million times that of a human or even any civilization's lifetime. Instead, we look at many galaxies at many different redshifts and work out the evolutionary sequence. We detect young galaxies at high redshift, intermediate-aged galaxies at intermediate redshift, and old galaxies at low redshift. In comparing these populations, we trace how the galaxies evolve over cosmic time. This statistical approach is surprisingly successful. We can see evolving trends in the properties of galaxies with redshift. Star formation rates were at their highest level at around z=2,3 and have decreased since then. Galaxy mergers were easier in the old days. Galaxies were smaller and more irregular at high redshift, progressively evolving into the spiral and elliptical morphologies observed today. The gas fraction in galaxies was greater in the past, so there was plenty of fuel for star formation. These and many other relationships tell a consistent story of cosmic evolution, he says. But it cannot tell us everything. Rare events, which are so infrequent that they might not show up in our samples, might be missed. Evolutionary trends may be misinterpreted if our samples are subject to biases that we do not know about. We may fail to connect different phenomena, separation in time, or observed of one object to another. Not being able to watch individual galaxies grow up is a fundamental constraint on cosmology, one that we can't get around by speeding up cosmic time. We are brought back to marvel at what we may. The CMB is effectively a picture of the entire universe at one cosmic age, 380,000 years. Each point in the sky shows us matter at almost the same age, aside from some minuscule time lags caused by the structure of the universe. This homogeneity means that we can treat the universe as a whole, rather than as a collection of disparate objects. We treat the universe as a single entity, and thus its large-scale properties are revealed. The fluctuations in temperature in the CMB are only about 18 microkelvins, 1 part in 100,000 of the average temperature of 2.725 Kelvin. These fluctuation patterns encode information about the very early perturbations in density that would later become galaxies. The pattern of fluctuations depends on physics at 380,000 years, including the competition between radiation pressure versus gravity, the speed of sound in the photon-baryon plasma, as well as the presence of dark matter. Cosmologists use spherical harmonics mathematical functions to analyze the CMB fluctuations, which characterize patterns on a sphere. The power spectrum of CMB fluctuations represents how much temperature variation takes place at various angular intervals. Large scales correspond to structures that were beyond the horizon at recombination, set by quantum fluctuations during inflation. Small scales correspond to acoustic oscillations in the primordial plasma, sound waves moving through the plasma before recombination. The location of the first acoustic peak in the CMB power spectrum is at an angular scale of roughly 1 degree. This scale is the physical size of the sound horizon at recombination and is the maximum distance sound waves could have traveled in 380,000 years since the Big Bang. The position of this peak depends on the geometry of space. In a flat universe, it is at L roughly 220. Gravitational lensing would make it appear at larger angles in a positively curved universe. It would be smaller in a negatively curved universe. Measurements confirm that the first peak lies almost exactly at 1 degree, implying that the universe is spatially flat, or nearly so. This flatness is actually somewhat surprising. One can imagine space having positive curvature as in the surface of a sphere or negative curvature as in a saddle shape, according to general relativity. The fact that the universe is flat within observational errors implies fine-tuning, unless inflation happened. Inflation makes the universe naturally flat by smoothing out any initial curvature on scales much larger than the observable universe. Higher resonances, the following acoustic peaks in the CMB power spectrum, contain further information. The ratio of odd peaks to even peaks is proportional to the baryon density, or ordinary matter. More baryons suppress the even peaks with respect to the odd peaks. Results indicate a baryon density of about 4.9% of the critical density. This value is identical with that deduced from the observed abundances of the light elements synthesized in the Big Bang, hence serving as an independent confirmation. There is also polarization in the CMB. This polarization is generated by Thomson scattering at the surface of last scattering. Free electrons scatter light with a preference for the direction perpendicular to the electric field, and so this creates patterns of linear polarization. There are two types of polarization patterns, called E modes and B modes. E mode polarization is generated by density perturbations and has been detected with high significance in CMB experiments. B mode polarization can be generated by gravitational waves, either the primordial gravitational waves from inflation or gravitational lensing of E modes by later intervening structure. The lensing B modes have been detected. The primordial B modes are still elusive, with many experiments hunting for them. Detection of primordial B mode polarization would be the smoking gun for inflation and revealing the energy scale of inflation. The amplitude of the B modes depends on the tensor to scalar ratio, which is a parameter that characterizes the relative amplitudes of gravitational wave perturbations to density perturbations. Current measurements put better limit on this ratio than 0.06, and if inflation did take place, it was not at energies higher than 1016 GeV. A host of experiments are seeking to find primordial B modes, including ground-based telescopes in Antarctica and Chile, balloon-borne instruments, and proposed space missions. The challenge is to distinguish the primordial signal from that of foregrounds, in particular emission from dust in our own galaxy. Dust grains aligned by magnetic fields emit polarized light and can replicate and mask primordial B mode signal. So how far we can see will naturally lead to what we can learn from the farthest things. It's not that the CMB is just far away. It is informative. In its tiny temperature and polarization fluctuations resides a treasure trove of information on cosmic conditions 13.8 billion years ago. Those conditions, in turn, constrain models of how the universe began, what it is made of, and how it is changing. The CMB ties observational astronomy to fundamental physics, to quantum mechanics, and to the most profound questions about being. Why is there a universe, to begin with? Why does it even have the properties that we observe? Why is it so big, so old, so smooth? The CMB also answers some of these. The uniformity is a consequence of inflation, which makes quantum fluctuations become stretched to cosmological sizes, thus erasing any pre-existing structure. The age is derived by determining the rate of expansion and extrapolating backward. The large-scale properties come from laws of physics acting on initial conditions given by inflation. But there are more profound questions still. What caused inflation? What caused it? What was before inflation? If that question even makes sense. Did time itself have a Big Bang? Or is there a state prior to which our universe burst forth? These questions lie beyond current observational capabilities. The CMB traces us as far as 380,000 years. Primordial gravitational waves could take us back to 1036 seconds. But earlier epochs, if there were any, are behind horizons that we may never penetrate. Cosmologists propose the universe is cyclic, eternally going through sequences of expansion and collapse. Others imply that our universe is just one of many residing in a vast multiverse, each governed by different physical rules and constants. And yet others raise doubts on whether time is fundamental or an emergent property arising from more basic quantum aspects. These are still speculative ideas, without any observational tests that could prove or disprove them. What we know for sure is that we can look back 380,000 years from the start, to when the universe became opaque, to the shell that radiated the CMB. Not only is this the latest we can see in electromagnetic radiation, it is arguably the latest we could see in any meaningful sense. After that, it's just speculation, stretching established physics to places where it may not actually be valid. The observation of the CMB itself is a direct observation of the very early universe. When CMB photons are received by a radio telescope, they are from a time when the universe was very different from today. The universe was smaller by a factor of 1100. It was hotter by that same factor and shining at a temperature of 3000 Kelvin rather than the 2.725 Kelvin of today. It was denser by a factor of approximately 1.3 billion, with matter in a very much smaller volume. Now in that early universe, there were no stars. There were no galaxies yet. No planets. No chemistry except hydrogen and helium. No complexity of any kind. But out of those simple starting points came the rich complexity we see in the universe today. Gravity has been working on tiny density perturbations for billions of years. Gas collapsed into galaxies. But by then stars had formed and died and polluted the cosmos with heavy elements. Planets formed from dusty disks around young stars. On at least one planet, and probably a great many others, life arose and evolved. The CMB photons that are going through your telescope right now began their journey prior to any of this happening. They journeyed through space as all this was happening. They seem to have witnessed the building up of cosmic complexity from primordial simplicity. And now they arrive, stretched and cooled by expansion, to tell us about that ancient beginning. This is the furthest thing we can see, 46 billion light-years away in comoving distance, 13.8 billion years old in look-back distance, at the edge of the observable universe, at the photon-based observational limit. It's the oldest possible light, the most distant possible signal, the furthest electromagnetic we can go in electromagnetic astronomy. It gave a cause for hidden questions, perhaps answers about the most profound considerations of how things are, or perhaps nothing, an empty void of significance. We don't know because we can't look. But everything within what we can see, everything inside the bubble defined by the CMB, is everything we can see. 2 trillion galaxies, each a sprawling star system. Countless planets, many that could support life. The cosmic tangle of filaments and voids, sculpted by gravity over billions of years. The CMB itself, which is isotropic to about 1 part in 100,000, contains the seeds of all structure. This is the universe we can know, the universe made visible by light, the end of the road. Anything is possible when you look at the night sky, as you're seeing light from objects at different times and distances, and a variety of ages and epochs in cosmic history. The moon that reflects the sun now is your current one. Your delay is only 1.3 seconds. Nearby stars to tell you about your recent past, decades or centuries ago. Galaxies that are billions of years away that you can see through telescopes are really telling you about the deep past. And filling all of space, undetectable to human sight, but visible to radio telescopes, the CMB takes you to the beginning, the moment of first light, the oldest attainable gaze into cosmic history. We can't see any further. That is the answer. The most distant we can see is the cosmic microwave background radiation, coming from a moving distance of about 46 billion light-years, emitted 380,000 years after the Big Bang, which has since been cooled to 2.725 Kelvin, which is the entire sky and consists of the oldest photons that we have ever seen. Farthest, oldest, deepest. Nothing is deeper. Older photons, it says, we cannot see. The CMB is the ultimate horizon, the final boundary, the farthest thing we can observe in our universe. But as we celebrate this accomplishment, we have observationally returned to the beginning of transparency, the Big Bang. We must also recognize what we cannot yet see. The universe before recombination was there, had a physics, was changing dramatically, but was opaque to photons. The first 380,000 years of cosmic history is a period so opaque to the electromagnetic radiation that no telescope for any part of that radiation can see through it. That's what nearly 300 millennia worth of evolution locked behind a door that we can never see through represents. During that first 380,000 years, it went through changes as radical as any that followed. It came out of the Planck epoch when quantum gravity was in command. Unification success when fundamental forces are unified. It went through an era of grand unification in which fundamental forces were unified. It overinflated, growing by a scale of at least 1026 in the blink of an eye. It cooled below the electroweak phase transition when electromagnetism crystallized out of the weak force. It saw the destruction of antimatter, but what was left was a tiny excess of matter which would ultimately create all that we are able to observe. Big Bang nucleosynthesis took place in the first few minutes and produced light elements from the neutrons and protons available from the baryogenesis. So about 75% of the baryonic mass was hydrogen. Roughly 25% became helium. Traces of deuterium, helium-3, and lithium. These have now been shown to agree with observations of the abundances of light elements to superlative accuracy, confirming strongly Big Bang cosmology, even though we cannot really see nucleosynthesis. Neutrino decoupling. At approximately 1 second, the universe had cooled sufficiently that neutrinos ceased to interact significantly with matter. These relic neutrinos should be all around us today as the cosmic neutrino background, yet we have not detected them, presumably because their interaction cross-section is infinitesimally small at our current energies. Detecting the CMB would provide a window on times earlier than the CMB allows, but the technical challenges seem insurmountable with today's technology. Matter and radiation had a comparable energy density 50,000 years after the Big Bang. Radiation previously dominated and led to fast expansion. After this epoch, matter dominated and decelerated expansion. This change affected the development of density perturbations, and so the ultimately formation of structure. Influence of matter density on the exact epoch of matter radiation equality is encoded in the matter power spectrum. This was all the way back before recombination, when photons couldn't move freely, before we could make any electromagnetic observations. We understand these early events through theoretical calculations and indirect evidence, not direct observations. The opaque time span can't be photographed, only possibly imaged by other messengers such as neutrinos or gravitational waves, if at all. This hidden early universe is a reminder that observation has its limits. There are frontiers beyond which we simply cannot see no matter how we look. One such boundary is the CMB, which is associated with the opacity of the universe prior to recombination. There is also the particle horizon, which is imposed by the finite age of the universe and the finite speed of light. It is the event horizon with which we see a third limitation, imposed by the accelerating expansion, is whisking away distant regions faster than light can chase. It is within these limits that the universe can be seen, and this is all there is in a sphere approximately 93 billion light-years in depth that is filled with the observable everything. It is a huge region, so huge that the human intellect cannot imagine its size, filled with more galaxies and stars than one could count. Still, it could be an infinitesimally small part of all being. It is reasonable to think that the universe beyond our cosmological horizon exists. There is no cause to think that space stops at 46 billion light-years. The same rules of physics that apply to this side of the ocean probably apply to that side. Galaxies are presumably assembled, stars probably shine, planets likely orbit. But it's all behind a veil. Information from such regions has not had the time to reach us. And maybe, if expansion continues accelerating, it never will. This cosmic humility also reminds us that what we can see, which is so much, may be only a tiny fraction of what there is to see. The most distant object we can see is not the edge of the universe, but is rather the edge of the observable universe, the limit of our cosmic light cone, the horizon beyond which signals have not yet reached us. How big the universe really is remains a mystery, and perhaps it always will be. Various cosmological models differ in their predictions for the overall structure of space-time. Some models portray a universe that is eternal in length, extending endlessly in all directions. Others correspond to an FLRW universe with finite volume, which is enclosed in on itself as the surface of a four-dimensional sphere. Still others suggest that our observable universe is just a bubble in a frothing, eternal, inflating multiverse, with a myriad other bubbles forever inaccessible to our eyes. The present data limit, but do not conclusively establish, the global topology. The universe seems to be spatially flat, which is what we'd expect if it were infinite, but that's not the only explanation. Flat space may be infinite, such as an infinite plane, or finite, such as a torus. The CMB power spectrum has no evidence of topology at observable scales, although subtle signatures may exist at the largest scales, where statistical uncertainties are largest. If the universe is infinite, then the most distant thing we can see is an infinitesimal edge in an infinite universe. Outside our horizon, there is unending space filled with unending galaxies, unending stars, unending possibilities for complexity and life. But if the universe is finite, then perhaps we see a significant portion of all that is. The observable universe could be 10% or 50% or some other large fraction of the total cosmic volume. So we don't know which is right. The most distant thing we can see looks the same if it's supposed to be in an infinite universe or a finite one. The CMB looks the same, galaxies look the same, the laws of physics work the same. Our measurements probe only the local region, and local measurements can only definitively determine the global geometry if that geometry somehow manifests itself as a local within-reach signature. And that fundamental uncertainty about cosmic extent just adds to the awe-inspiringness of the astronomy. We have taken measurements of the universe we can see with incredible accuracy. We know its age, size, composition, and geometry to several decimal places. But we cannot tell if the entire total of existence is finite or infinite, if all that we see is everything there is, or a proverbial drop in the bucket. If our universe is a mere bubble, or it contains countless bubbles among breath after breath of air. So the answer to the question, how far away is the furthest thing we can see, turns out to be connected to some of the biggest questions about existence. How big is reality? What's beyond observation? Are there limits to knowledge itself? But the 46 billion year distance for the CMB answers that very specific question, and yet triggers even larger questions about the nature of the cosmos. With tools that allow us to look further back and study more distant things, we are bumping up against these final frontiers. JWST is looking at galaxies at redshifts of almost 20, showing us the universe when it was less than 200 million years old. Telescopes of the future may even get to whiff higher redshifts towards the cosmic dark ages. Gravitational wave detectors may hear primordial echoes of inflation. Neutrino detectors may someday beat the CNB. Every advance in our ability to observe takes us just a little bit further, back just a little bit deeper into the cosmic record, answering some questions while raising others. But the deep limits remain. The baryon-photon fluid characteristic of the pre-recombination universe prevents electromagnetic observation prior to 380,000 years. Because of the finite age of the universe, no one can look back further than the Big Bang, at least in time. Light speed limits us to the particle horizon for any observations. These are not technical challenges to be solved in the future. They are a consequence of cosmic geometry and physical law. No matter how powerful, no telescope can penetrate the opaque plasma of the early universe. A detector, however sensitive, cannot catch signals that have not yet arrived. Sophisticated tools cannot peek past the particle horizon, since they have yet to receive signals from those regions of space-time. The furthest object we can observe is the CMB, and the CMB should continue to be the furthest object we can observe using electromagnetic radiation for the entire time that astronomy is done by either us or our progeny. Future measurements may bring the characterization of the CMB to a higher level of precision by mapping its polarization at higher accuracy, by identifying subtle signatures in its frequency spectrum, and by observing its anisotropies with finer angular resolution. But no observation, now or in the future, prospectively probes beyond its current view of the universe, the surface of last scattering at 380,000 years. There is a certain pleasure to that finality. We have reached the end. We have seen the earliest photons possible. We have gone as far as photons can. This has an answer, not a provisional answer that will wait for more powerful telescopes, but a definitive answer that is determined by the physics of the early universe. The fact that the CMB is the farthest we can see using electromagnetic radiation, period. Nothing before that ever emitted photons that could reach us. There is nothing that is further away that you can eavesdrop on via electromagnetics. This is one of the most amazing accomplishments of human beings. The extent and age of the universe were unknown for nearly all of humanity's existence. Various cultures devised alternative cosmologies, most extremely erroneous by modern norms. The scientific revolution starting in the 1600s brought about procedures for sense-based inquiry, but indirect perception of the cosmic scale was not feasible for centuries. It was only with the 20th century that astronomical methods developed to the point where cosmic distances and ages could be measured. The discovery of galaxy recession by Hubble in the 1920s also revealed cosmic expansion. Predictions by Gamow in the 1940s indicated the CMB should exist. Those predictions were confirmed by the discovery of Penzias and Wilson in 1964. Kobe in the 1990s, WMAP in the 2000s, and Planck in the 2010s successively improved our measurements of the CMB and what it means. Each one took us a little closer to answering how far we can see, how old the universe is, and how big it has gotten. Each measurement adds precision, narrows parameter space, tests predictions. Over decades, The accumulating data turned cosmology from speculation to precision science. Today we can say with certainty that the CMB is emitted from a moving distance of 46 billion light-years, is emitted 380,000 years after the Big Bang, and is the farthest electromagnetic signal that we can detect from Earth. This information connects us with the universe in a very deep way. When you realize you're looking at the universe itself, at 380,000 years old, the furthest thing you can see, you comprehend your role in a vast cosmic tale. You consist of atoms which were forged in stars that formed billions of years post the emission of the CMB. You live on a world that came together billions of years after the first galaxies formed. Using telescopes, you examine photons that traveled for almost the entire lifespan of the universe to find you. The light you are detecting from the CMB is older than the Sun, older than the Earth, and older than our galaxy as well. These photons predate everything recognizable, everything that's in your house. They were around when the universe was a hot fog of matter and radiation before stars or galaxies or any complexity. And they crossed 13.8 billion years observing, building, the cosmic structure, coming to today to tell you about that ancient beginning. This is as far as we can see, the answer to the question, the edge of observation, the end of our cosmic light cone. The CMB is at 46 billion light-years, emitted 380,000 years after the Big Bang, cooled by expansion to 2.725 Kelvin, and fills the entire sky with the oldest photons we can observe in the universe. This is as far as electromagnetic observation can go. That's the ultimate horizon. This is the distinctest thing we have ever seen in the universe.